No, thank you. I wanna start by thanking the organizers for accommodating my talk and making it possible. I also want to say though that I'm really sorry that I'm not there in person because all of the previous talks have seemed super cool and I've been following along, but it's completely different to be in person. So hopefully that will happen at some point. Yeah, so for today, I wanted to focus on the question of measuring and looking for local type primordial non-Gaussianity, which is to say deviations from the early universe Gaussian field assumption. And in particular, I will focus on several different new probes that have been proposed in the last few years that allow us to circumvent some of the known issues in measuring these kinds of deviations and also some of the challenges associated with these probes. So first of all, an obvious question, why do we study local type primordial non-Gaussianity, especially with large-scale structure? An obvious reason is that the very exciting limit that we want to breach is that of measuring the FNL parameter, which is associated with the primordial non-Gaussianity to a level of order 1. And why is that exciting? Because if we measure it with these small error bars and we find a deviation from 1, that indicates a failure of single field inflation models. So it basically would rule out a huge class of models, the simplest inflationary models, and it would make the universe even more interesting. And so the interesting thing is that if we look at CMB constraints, because they're two-dimensional constraints on the sky, there is a limited number of modes, and we are actually stuck with sigma FNL of about 5. But with large-scale structure, we can breach that and reach these limit of 1. And so how do we do that in large-scale structure? So the formula that you see in the bottom here describes what happens in the presence of primordial non-Gaussianity through this FNL parameter. You see that you start seeing deviations on the largest possible scales depending on what the value of FNL is. And this is just in the galaxy power spectrum. However, there are a couple of quick caveats to this kind of measurement. The first thing is that on large scales, we are dominated by cosmic variance. So the fact that we are limited by volume means that here it's really hard to start to see deviations from the lambda CDM prediction. The other issue is shot noise. So this is demonstrated here by this straight constant line, which is obviously an approximation, but the idea is that if we have sparse samples, this shot noise increases, and it can actually make it difficult to measure the power spectrum on large scales as well. And so we have this tug of war between trying to find samples that are far away enough such that we can encompass a lot of the volume, and at the same time, not that sparse such that the shot noise term is not dominant. In addition, there is an unknown bias parameter B phi that is associated with this measurement. So if you look at the formula here, there is a perfect degeneracy between B phi and FNL. So in other words, if we want to measure FNL in an unbiased way, we really also want to constrain B phi, this bias parameter. And so what are some of our ways of moving forward? B phi can be measured, for example, as a function of observable properties. And there have been a number of works, especially by Alex Barrera and Elizabeth Krause, that have pointed these kinds of, so they have pointed issues with our assumptions of B phi that I will go over in a little bit more detail in a minute. And at the same time, they have proposed ways forward. And I would like to give you a short extension to that proposal in some recent work of ours. Then a second way of moving forward is to look for so-called zero bias tracers. And I will say why that's favorable. And this is ongoing work currently with a master student that I will also talk about. And then finally, I will just briefly mention an exciting new way of approaching these large-scale structure, which is through the use of velocity fields and the reconstruction of velocity fields through things like the kinematic Sonia-Zoldovich effect. Okay, so let's start with just introducing the simulation suite that I'm using for all of these above mentioned projects. So this is AbacusPNG. Advertising it in one slide here just to say that it's a publicly available suite of simulations that include local type Primordial Non-Gaussianity in a 2 gigaparsec over H box, and that have pretty good resolution. And okay, and so for us, the first question that we wanted to study was how much does B phi deviate from the so-called universality relation? So people typically make the assumption that B phi is trivially related to the large-scale bias, to the linear bias through this kind of equation. And so we were interested in first checking this result through looking at halos and splitting them into low and high concentration halos. And indeed, you see that there is a pretty large scatter around this mean value that corresponds to the universality relation. And so this scatter here, the question is, how can we capture this scatter such that we can reduce the uncertainty on B phi and hence the uncertainty on FNL? And my cat is in the way, but I guess the solution that we came up with in this paper was to essentially measure not just B1, but also measure the other bias parameters and come up with a linear approximation that just multiplies these bias parameters by some coefficients and gives us a good prediction of B phi. So the idea is, okay, like we know that B1 itself has pretty large scatter, but if we now measure all of these bias parameters, can we reduce that scatter? Can we break this degeneracy, or not degeneracy, but can we just add more information to this B phi constraint? And so here I'm just showing this for a fixed, for a set of halos at fixed halo mass. And the question that we wanted to see here, to ask here, is if we look at the plane of B1 and B phi, and then B2, B phi, BS, B nabla, all of these second order bias parameters in EFT, do we actually see, can we see which parameters are the most correlated with B phi? And so you can see that B1 indeed has pretty strong correlation, coefficient of about 64% at fixed halo mass. And then this is not as strong for these other parameters. But the interesting thing to me was that if we look at B nabla, we actually see that we have a very strong correlation coefficient of about 94% with B phi. And we investigated this a little bit further, and we found that the reason was that B nabla and the concentration are actually very tightly correlated. But there is one caveat here, and that is that here we are looking at the fixed halo mass. And so if we look at a realistic galaxy sample where we actually mix a bunch of different halo masses, we see that the picture becomes a little bit more complicated, and yet the combination of bias parameters, and so here what I'm showing is the reduction of the reduction of uncertainty on B phi in the case of using all bias parameters versus using just B1 and including assembly bias and a bunch of other selection properties. And what we see is that actually this reduces quite a bit if we put in all of the information from the other bias parameters and try to constrain B phi. So okay, so this was my first thing that I wanted to mention. And if we now for a second say that we have solved this issue with B phi, which is, as you will see, not as trivial, let's ask the question of, can we reduce the noise on FNL, or can we reduce the constraints on FNL? Can we increase the constraints on FNL by, for example, looking at these zero bias tracers. And so this is work led by a master's student, Amius Marshall, who's been doing a really, really great job with this. And the motivation here is that the cosmic variance is proportional to the b squared times times the matter power spectrum. And so if we reduce the bias, we are actually measuring b phi on large scales. This is just kind of the intuition for it. And the question is, can we find a sample that has very low bias and hence very low cosmic variance, and at the same time that has small shot noise, or in other words, is a high density sample. And this is actually quite promising for both SPHERex and DESI 2, because they will both have these high density samples and will be able to split galaxies in more ways than we typically can. And so here I'm just pulling out the equation from Emanuele Castorino's paper from 2018, where you can see that the constraint on FNL, which is the inverse of the Fisher element here, is proportional to b squared divided by b minus 1 squared. So the same idea that if we lower b squared, then we increase or we decrease the error bars on FNL. Okay, and so how do we construct that in practice? How do we look for these zero bias tracers in practice? So here's the heuristic that we came up with for this project. We take the galaxy, the observed galaxy over density field in redshift space. We smooth it with some constant smoothing, say of 10 megaparsecs over h. And we then associate each galaxy with a density based on what a voxel it lives in. And then we select the lowest X% of galaxies according to these densities. And here I'm just showing what the smoothed over density field looks like versus the galaxy over density field. So you can see that the galaxies live in mostly the highest density regions, and yet we can still draw the distinction between galaxies living in lower density regions and higher density regions. And so if we do that, there are of course a number of parameters, free parameters to choose here. So one is, what is this X percentage? Do we split the galaxies into 40% of the lowest density or 75% of the lowest density? What is the associated, what is the smoothing scale? All of these kinds of free parameters matter. And so what Amius did was he created a huge table, and I've spared you the effort of looking at that table and just shown a small section of it. So he created a huge table with all of these different configurations of different smoothings and different ratios of the selection of galaxies. And he studied essentially what happens to the constraints on sigma FNL, and compared it to the case where we don't do this kind of splitting of low density versus full sample galaxies. So if we don't do any of these kinds of splittings, we find for this particular box, Abacus box of 8 megaparsecs over h cubed volume, we find a sigma FNL of about 28. And we see that if we now start looking at these lower bias samples, and this is the bias that we obtain for each of these cases, we do see a pretty large improvement on the constraining power. And in particular, for this final configuration with 75%, we see that there is an improvement of about a factor of 6. And it is non-trivial that actually it's not the lowest bias sample that gives us the best constraints, and that has to do with the shot noise of that sample, but I won't go into that much detail for this. One interesting challenge though is that in the previous calculations we assumed that b phi is given by the universality relation. And as I mentioned before, the universality relation is not always a very good approximation, especially if we have interesting selection effects going on with our galaxy sample. And so we were also interested in using the separate universe approach to measure B-phi and compare that with the universality relation prediction. So the separate universe approach is where we take another simulation with a different value of sigma 8 and looking at the differences between galaxies living in high sigma 8 versus low sigma 8 universes, we can actually infer a measure directly B-phi. And so in doing so, we found that actually the universality relation is pretty far off from what the separate universe relation finds for a bunch of these different galaxy samples. And this is something that we're still investigating, but it's kind of interesting to know that that's something that we need to also worry about. And another interesting question is, in choosing these low bias samples, we're also choosing void regions which have, as we know, different velocity bias. So that might also be a complication to the analysis because it might lead to a different effective growth factor. So far, we haven't really found that to be a problem, but this is also still ongoing, and hopefully we'll have a paper coming out soon. Okay, and finally, in the no time that I have left, I just wanted to shout out some work done by some collaborators of mine, including Fiona McCarthy, and who is looking at reconstructing radial velocity fields via kinematic Sunyaev-Zoldovich effect. And so the idea here is that the kinematic Sunyaev-Zoldovich effect is the product between optical depth and line of sight velocity. So if we cross-correlate the temperature from a CMB map with the galaxy over density field, we can actually obtain a measure of the velocity field. And what's nice about the velocity field is that if we now look at the shot noise term for the velocity field, it's shown in red here. It is way more favorable compared with the shot noise term in the typical galaxy case, in the sense that on large scales, we see that the noise is much smaller, and that allows us to measure these large scale modes much better. And so we are currently investigating this in more detail. But as you can see, there is also another degeneracy here with the optical depth parameter. So you can see that we're not measuring purely the velocity field. We're actually measuring that plus times some bias factor here. And this is something that we're currently investigating for Fiona's next paper that's hopefully going to come out soon, is this question of how big is this bias here, which is actually quite dependent on baryonic feedback because it measures the optical depth correlation with galaxies. And depending on basically if we have very strong feedback, this bias can deviate very strongly from 1, this bias parameter, and otherwise it might, it's actually closer to 1. And all current analyses are finding very low values of the bias, which is sort of in line with findings in, for example, stacked KSZ measurements, which are also indicating some strong baryonic feedback. But all of this is kind of currently under investigation. And I think it's just kind of cool to me that there are all of these parallels between baryonic feedback and then measuring primordial non-Gaussianity on the largest scales possible. And yeah, so I just want to maybe leave you with my conclusions and welcome any questions if you have any. But yeah, I think it's exciting to measure primordial non-Gaussianities, and I think there are several exciting paths forward to doing so. Thank you, and thank you to the organizers again.